Welcome back, everybody. Today we're in section 1.7, transformations of functions. Transformations can be really helpful in graphing some more difficult equations. So let's start looking at the concept of transformations and how a function reacts when we add, subtract, multiply, divide to that function. I always try to explain transformations best by using an example. All right, so for example, let's take a basic function like y equals x squared, and we'll call that our parent function for now. When we talk about moving a function around a graph, it's always in relation to a parent function. All right, so with the parent function, we can make a quick graph by creating a table of values or just drawing the graph if you know the shape. All right, and our parent function graph is going to look something like this. So if I go -2, 4, -1, 1, 0, 1, and 4. And then I'm going to all right. So the question is, what happens if I say y equals x squared, let's say plus 3. Do plus 3. That's enough. Now you could do another table of values. However, that usually takes a long time. So what we're going to assume is that the behavior of the function at plus 3, there'll be very similar behavior if we did, let's say, plus 2, plus 4, plus any number. All right. So we're going to make a table of values now, but we're going to kind of get an idea of what the behavior is and see if we can generalize that behavior. All right, so let's just take a quick look. So if I say -2, that's now 7. -1 is now 4. 0 is now 3. 1 is 4. And 2 is 7. So I'm going to draw this graph, but I'm going to draw it in green so we have just a contrast. So there we go. I'll go to, okay. So -2, 7, 1, 2, 3, 4, 5, 6, 7 up here. And then -1, 4, 1, 2, 3, 4, about there. 0, 3, and 2, 3, 4, and 7. So basically our function, other than my poor drawing aside, looks something like that, where each point is basically translated up 3 units. So if I had, let's say, y equals x squared plus 2, y equals x squared plus 1, in this case, my points would be translated up 2 units from the parent function. Here would be translated up 1 unit from the parent function. So we can say when it looks like this, when it's adding something outside of your parent function, my parent function is x squared, I'm adding something onto the end of my parent function. It goes up that many units. So in this example, my function is translated up 3 units. All right. So let's use the same parent function. Y equals x squared. And I'm just going to create the graph now. We already did the table of values. All right. So I don't really need to do that again. All right, now the question is, what happens if I subtract on the end of my parent function? Well, if adding moved it up 3 units, we can assume subtracting will move it down. All right, in this case, 4 units. But let's do a table of values just to make sure. Remember, the table of values is great because it always works. So if you're ever unsure about something, make that table of values. As long as you make the table correctly, it always works. So let's say -2, negative squared. So that's 0. -1. -1 squared is 1. 1 minus 4 is -3. 0, -4, 1, -3, and 2, 0. So again, I'm going to make this in a different color. Make it in green once again. So 0, 1, 2, 3, 4. I have 2, 0 right there. And there is my sketch. So notice from here down, I'm translating down 4 units. From here down, I'm translating down 4 units. From here down, I'm translating down 4 units. 4 units, 4 units. So again, if we're subtracting on the end of our function, all right, then we're moving down that many units. All right. Now, notice I put a stress on the end of our function, all right? I want to give you a slightly different example. I'm going to use the same parent function. Now, notice I'm using the same parent function multiple times. I'm doing that to kind of cut down on our legwork in the beginning. We've already done this graph. We know what it looks like. But any function could be known as a parent function. What you'll see before this lesson is out is I'll use a number of different parent functions. But what if we had something like y equals x minus 2, the whole thing squared? Am I now subtracting off the end of my function? Or am I subtracting right in the middle? Right in the function is x squared. Now remember, this x is just a placeholder. I'm filling it with x minus 2. So I'm subtracting right in the middle of the function. What do you think is going to happen here? Well, let's make a table of values and see. So why don't we do this? Why don't you pause the video for just a second, make that table of values, and let's compare notes on the back end. All right, not only did I make a table of values for this particular function, but I also drew my parent graph. Once again, I'm going to draw the new graph in a different color. So for 4, 3, 1, 2, 0, 1, 1, and 0, 4. So we'll come down and go up. Now my function was not translated up or down. It actually moved right. So it translated right this many units. So right 2 units. All right. So might be a little different than what you were expecting. You might have been expecting that it would go left because there's a negative there, but it actually indeed goes right. But let's try it the other way. All right, so let's say, right, y equals x squared, parent. And let's do y equals, let's say, x plus 4 squared. Now, again, we're adding 4 in the middle of the function. So why don't you pause the video? Let's make that table of values, and let's compare notes when you come back. All right, so here's my table of values compared to yours, but let's make a graph, and I'm not going to graph the parent function. Now, we've seen that enough, so I'm going to say -2, 4, -3, 1, -4, 0, 1, 4. Now again, anytime I'm asking you for a graph, it's always a sketch. So not my best effort there. I'm going to try to make that a little bit better. Does not have to be precise, just has to be mathematically accurate. So that is most definitely accurate. And what happened to my graph compared to that parent function that we've been graphing the whole time? Well, what we see is that when we add inside our function, we actually move it left to 4, right? Left, in this case, 4 units. If we had +3, it would have been left 3 units. If we had 5, it would have been left 5 units. All right. So while these are great in a vacuum and they seem fairly easy, right? I would say a fairly easy quiz question I could give you would be, graph the function f of x equals x plus 3 squared minus 5. So why don't you do me a favor? Let's pause the video. Think about how you would graph this. You could always use a table of values, but give a try to not using a table of values. Use the concepts that we just went over and see how your graph goes. We'll talk about an answer on the back end. All right. So maybe you used a table of values, maybe you didn't. Or maybe used a hybrid of both. I'm actually going to show you a hybrid of both because this is the way I would attack this problem. All right, the first thing I would do, right? Remember what my parent function is, y equals x squared, right? It has a vertex at 0, 0. And then I want to look at my transformations. I'm moving 3 to the left and 5 down. So I want to move 3 left, 5 down. So where's my new vertex? My new vertex 3 to the left would be -3 and 5 down would be -5. So from 0, 0, I'm moving 3 left and 5 down. My new point is 3, -5. Now from here, if you're a good drawer, you could probably draw a very good parabola opening upward that would get you credit. As you can see, I was never the best drawer. So what I probably would do would be to say, okay, now I want to make an XY table because I can move through an XY table pretty quickly with a function like that. But what I'm going to do is, I already know one of my points. I'm going to put that point in the middle. All right? And I'm going to say, as long as I got a couple of points on either side, I should get a good drawing. So I already did this, so -4. You can check my work. -1. 2 is -4. -1. And then we could sketch a quick graph. One, 2, 3, 4, somewhere around there. 3, -5 down there. 4 and again, just a sketch and a sketch on a computer, which makes it a little bit more difficult, but you get the idea. And with my table of values, right, I'm showing a little bit extra work in an effort to make sure that I am getting the most accurate graph I can get. All right. So the next idea about acting on a function is called compressions and stretches. All right. And I want to use a new parent function. I told you can use anything you want as a parent function. So I'm going to use the absolute value of x. And basically what the absolute value of x looks like, vertex again at 0, 0, 1, 1, 1. Freehand, that's about right. All right. But what if I had something like y equals 2 absolute value of x, which means I'm multiplying, but I'm multiplying outside of my function is absolute value. I'm multiplying my value outside of that. All right. So how is this going to look? Well, we can make a quick table of values. To just take a look, I can say -1 is going to be 2, 0 still 0, 1 is now 2. And let's overlay our very quick table on our graph. So -1 instead of 1, it's now 2, 0, 0, and 1, 2. And there's my graph. All right, so it is a horizontal. Now notice, from my parent function to the new function, horizontally I compressed. If I put my hands on either side of my parent function and I pushed in, meaning compress, all right, if I pushed in, I would get the new function. Now the other idea, all right, is vertical. Basically what it's saying is that if I grab, let's say I grab the arrows of my parent function and I pulled up, it would be a vertical stretch because I would get the new function. All right. So I like to use vertical. So anytime this value, I'll call that value A, is greater than 1, it's a vertical stretch. All right. So let's think about the idea of a new function. So I'm going to use the same parent function. But my new function is multiplying times a half. All right. So let's make a quick table of values for the new function. And I'm just going to put a couple of values in. -1 is a half, 0 still 0, 1, let's pull that up. 1 is a half. All right, so again, I'm going to graph my parent function quickly, just so you get the idea of it's happening in relation to this. So there we go. All right, now this new function, I'll graph in green. So it's 1 up a half, 0, 0, up a half. You see how it gets that much wider? And that would be a vertical compression. If I took my foot and I stomped on my parent function, it would go down to the other, it would be compressed, go down to the other function. All right, and that's going to be true, again, I'll call that A. Anytime A is between 0 and 1. All right, I think I'll take that equal to away, because if it's 0, you don't have a function at all. All right. Let's quickly talk about some reflections. All right, let's go back to our old parent function, right? Y equals x squared. All right. Now the new function I want to graph negative x squared. So let's make a table of values and see what happens with this new function. All right. So pause the video, make that table of values, and we'll compare our answers on the back end. All right. So why don't you compare your table with mine? All right. And if it does not read the same, definitely check your work. Because if you take negative 2 and plug it into x squared, that's positive 4. And then multiplying times negative 1 gives you negative 4. You got to remember those order of operations. But let's take a look at what happens on our new graph. Negative 1, 1, 0. Okay. So again, we've graphed our parent enough to know that it is a parabola opening up. This happens to be a parabola opening down. So when we put a negative in front of our function, write this down, when we put a negative in front of the function, it's a reflection over the x-axis. All right, let's take a look at one more. I want to use blue. Blue shows up just a little bit better. I'm going to use a new parent function. Is going to be y equals the square root of x. Now, let's graph y equals the square root of x before we go to our new function, just so we can take a look at the graph. Make a quick table of values, because my table has to start at 0 and go up. It can't go negative. So 0, 0, 1, 1, right? And then I'm just going to skip to 4, because square root of 4 is 2, all right? You could put 2 and 3 in there, but square root of 2 and square root of 3, kind of tough to graph. You'd have to estimate. So I'm just going to use, I can even use 9, 3. So 0, 0, 1, 1, 4, 2. And remember, it doesn't go either way. It just goes off to the right. All right. So that's the way our parent function looks. Now my new function, which I'll do in green, is going to be y equals the square root of negative x. And what this is going to do is it's putting a negative inside my function. Now you might say, hey, wait a second. We're not allowed to do that. But you are. It all depends on what your domain of x is. So now when we do our table of values, right, basically what we're saying is that x can't be a positive number anymore, right? It has to be 0. It could be negative 1, because if it's negative 1, I'm multiplying times negative 1. Negative 1 times negative 1 is positive 1. And then I'm doing the square root. Remember, this is kind of like it's inside the parentheses, right? So that's 0. Square root of 1 is 1. Square root of negative 4 is 2. So what do we see when we make this graph? I got 0, 0. Oop. Make a better graph than that. And I'll go down like this. But notice, from the parent to the new graph, what happened when I put a negative inside my function? When I put a negative inside the function, it's a reflection across the y-axis. All right. So here's another quiz type question I can give you. Find the function that is finally graphed after the following transformations are applied. All right. So I'm just going to write out the transformations. All right. So you're going to find the function that is finally graphed after the following transformations are applied to y equals absolute value of x. All right. So that's our parent. All right. So the first transformation is left 2 units. Second transformation is up 3 units. And the third transformation is reflect about y-axis. All right, and remember, we are just finding the new function. All right, why don't you pause the video for just a second, give it a try, and we will talk about the answer when we get back. All right, so hopefully you took a look at this problem. Now, the way I would tackle this is literally one transformation at a time. So my parent function is y equals the absolute value of x. The first transformation is going left 2 units. So I'm going to use a different color just to contrast. And I'm going to say after transformation number 1, I have y equals, now remember, if I'm going right or left, I've got to put my inside my function. So I'm going to say x plus 2 inside the absolute value units. Not my final answer, just an answer along the way. After the second transformation, now here we're going up 3 units. So I'm going to say y equals absolute value of x plus 2 plus 3. Now remember, this x plus 2 is a quantity, right, inside my function. And those parentheses don't make a difference right now, but they are going to help me with transformation number 3. Now remember, transformation number 3, I have to put a negative inside my function, y-axis. Negative x plus 2 plus 3. And this is the function that we would finally graph. Now, there is also a possibility that I could ask you to graph that function. I'm not asking you that right now. Just finding the function for now is enough. All right, this is kind of a long lesson, but not too bad. Thanks for listening, and I'll see you guys next time.